Hello, my name is Mark Case, and I'm the Science and Motion Director at Lehigh Carbon Community College. Today, we're going to be taking a look at how to determine the concentration of a colored solution using the techniques of spectroscopy. In order for you to be able to see what devices we're going to be using, I'm going to go to share screen and let you see the things that we have set up. And we're going to be utilizing a Vernier Go Direct colorimeter. The Go Direct just means that it has the ability to connect via Bluetooth to your device, whether it be a computer, PC, Mac, or a Chromebook, or some other device such as an iPhone or iPad or an Android machine. Or you could also hook it up using a USB cable. This particular device has 4 different LEDs. The wavelengths are 430 nanometers, 470, 565, and 635. And basically, it's changing the color of the LED that is going to be passing through the sample that will go down inside the chamber. We start by taking a cuvette, which is either a square, or you might also have a round, like test tube style cuvette, but you place it down inside the chamber with just distilled water in there. And then what you want to do is you want to set it so that it's reading 0. The program that we're using, graphical analysis, is set up for doing in events with entry, adding concentrations. Right now you can see that it's already reading 0 for a value. So that's good. We don't have to recalibrate it, but you can hit the calibration button and it will set it to 0. I have made up some solutions that we're going to be dealing with of copper sulfate. The stock solution is 0.4 molar that we're going to be working with. And when I place it down inside here, you'll be reading an absorbance value that is based on how concentrated that solution is. The other factor that determines what amount of absorbance it has is the depth of solution, or what they call the path length. How far is the light traveling through that cuvette to get to the other side? And in this case, it's 1 centimeter is the amount of path length that we have. When I start collecting data and take a look at running through this, it's going to say, do you want to keep the sample that you've now placed inside there? And when I hit the keep button, it will then ask me for what concentration would I be using. So I know that it's a 0.40. Now you'll notice that besides absorbance, it also is giving us a percent transmittance. There's a correlation between the two. It's a logarithmic function based on 1 over t, the logarithm of that being related to the absorbance value. So your teacher can talk about that more if he wishes, he or she wishes to discuss that. So we keep the point. We have 1 data point that's up here. I've gone through a series of dilutions by taking the 0.4 and then adding some water to it, so that it was 8 milliliters of 0.4 with 2 milliliters of water to make 10 total. You can see that when I put it down inside, the absorbance there is less. It's 0.67 instead of 0.85. So this concentration, based on being 0.8 of the 0.4, becomes 0.32. And I keep that point. Now notice it's way down here over on the other side because I have only 2 data points, so it's separating those and spreading them out in the space that's available. When I keep going through my other dilutions that I've gone through and created, I have a 0.24. Let's see what that value gives us. Wait for it to stabilize. Looks like about 0.53. So for that particular one, we're going to put in that it was 0.24. So that was 6 milliliters of the original solution plus 4 milliliters of water. Then I have 0.16. I'll let you figure out what was the amount that you'd have for that value to be a 0.16 from the original 0.4. So I'm going to keep that, and that'd be a 0.16. And then I did 1 last dilution, so I'd end up with a 0.08 molar. Wait for that to stabilize and keep that value. And that was 0.08. If I stop data collection at this point, I now have what appears to be a fairly straight line. So down here on the left, I can choose to add a curve fit. And the option, one of the obvious one is linear, but there's other options I could choose from. Let's just stick with the linear and see what we get. And it gives us a y equals mx plus b expression. This can be used to determine what is an unknown. So we have an unknown solution that we don't know what its molarity is. Let's throw that inside here once and see what the absorbance of that unknown is. The unknown has an absorbance value of 0.40. Now, I don't want to save this value because I don't know what the molarity is, but I do want to record that value. So down here under the graph options, I can do an add an annotation. And what that will allow me to do is to say that the unknown absorbance, in this case that we tried, it was 0.40. And then I can move that anywhere on my curve that I want to. Let's just save that. So save as. It's going to let us put in a identification of what this is going to be. So we're going to say this was CuSO4, copper sulfate, copper 2 sulfate that we're working with, and concentration. And then if I save that, I now will be able to look at this later on and do some analysis with that. Where you save it at, pay attention to where you're going to put that. You can put it on the desktop. I'm going to put it into the my LCC sim records that I have, so I know exactly where it's going to be, and I save that. And now I can come back and use that to do my analysis and figure out what my unknown will be. Now let's assume that you don't have all this fancy equipment. The graphical analysis app is for free, so anybody can get that, but let's assume that we don't have it. So let me just quit graphical analysis. And let's say that all we have is basically the two solutions. The 0.4 molar, my standard, and my unknown. Now, a second factor that's associated with these is that they are basically going to be absorbing depending on the depth. I mentioned that. So if I look at them side by side, it looks like the unknown is lighter in color and not as dark as the actual known value is. If I take off the lids and instead of looking through them where the bottles are about the same thickness, but instead let's change my perspective so that I'm looking down into the solutions. Now you can see very clearly that the one on the right-hand side does shift a little bit depending on the amount of background light that you're getting, but the one on the right-hand side is definitely darker in color. So it's because the depth at which it's traveling through contains a greater number of copper ions. Copper is what's actually creating the color. So you can tell much more easily by looking down through the equal depth that the one on the right-hand side, this guy over here, which is my standard, is much more concentrated. So what I would want to do is I could remove some of the solution from the standard. As I take some of that out, it doesn't really look that much lighter until I keep removing more and more and more. So I have to continually take some out of the solution that's more concentrated until the adjustment of the height times a higher concentration looks the same color intensity as where we have the one that is of a lower concentration with a greater depth or height to it. Slide it over just a bit. And I would keep doing this until, to my eye as I'm looking down through, or in this case to the camera, it appears to be the same. Now your eye and your camera might have a slight difference in opinion on what it looks like to you. Your eyes are actually much more sensitive than the camera to be able to figure this out. Also, if you lift it up off the paper a little bit, the amount of shading coming up from underneath makes it look a little different. To me, it looks like it's still a little darker in the 0.4 molar. Maybe still a little bit darker yet. And I continue until I say, they look like they're about the same appearance. I have a pretty close situation where they're almost the same intensity and color. When I am satisfied that the color intensity of the unknown, which has lesser molecules per volume, but a greater depth that it's passing through, is absorbing the same amount of light as the one that has a higher concentration but less depth. Okay. Then at that stage, I would say, okay, now they have the equivalent amount of particles per the depth of solution. So what I would need to do is to view these from a front position, looking straight at them so that I can measure where the depth is of these two using just an ordinary metric ruler. So let me readjust my camera angle. I'm going to have to lift them up so that you're going to be able to see it a little bit more clearly. Let's take the one that's the unknown first. So I set my ruler along the bottom and I adjust the height position so that I'm looking straight on at it. And I get a reading of where that looks like it falls. So even though you are looking at it and you see, oh, that's not quite straight at the bottom, but actually that's a parallax error. We're looking downwards. So it looks like the metric ruler is below, but it's actually level with that. If I bring it up a little bit, we're somewhere close to about 4.1 as a value for that one for my known. And then the depth of the other one, the unknown. Again, let's get it set at the bottom so it looks like it's at the same spot. And then get it even at the top. Oops, sorry, I moved that. You can do this much more accurately than I'm trying to do here very quickly. So we had about 4.1. And this value looks like it's about 8.5. And that ratio of 8.5 to 4.1 would give you an idea of what the concentration is of the unknown, because its depth times its concentration gives you the same amount of particles absorbing as the 0.4 molar times its height that you have, or its depth. So 4.1 times 0.4 equals about 8.5 times whatever that unknown concentration is. And you can solve for that. So that's a quick and dirty way of trying to do that. A third method is to actually use a spectrophotometer that will give you a full range of radiation from visible light, from about 380 all the way up to about 770 or so. Gives you your range from your purple colors all the way up to your reds. The reds are somewhere around 650 to 770 before it starts getting into infrared. But let's do the analysis, see if you can figure out your concentration of your unknown by the two methods, and good luck. Your teacher will help you out if you have any questions.